Welcome to the Chapter 6 of the Oil and Gas Engineering audiobook. This chapter presents the work and the deliverables of the Safety and Environment discipline. An oil and gas plant safety is primarily ensured by reducing the likeliness and the consequences of leaks, of loss of containment. This is done by working in a number of areas such as detection and protection, which are listed by the Safety and Environment engineer at the start of the job in the safety concept, also called the safety philosophy.
This document is called a discipline design specification. It is a document that each discipline should issue prior to start its design. It lists all the criteria that the discipline will use in its design work, such as applicable codes and standards, and so on. We will review each of the headings of the safety concept. First of all, hazard identification. The identification of hazards to which the plant could be subject is done during a multidisciplinary review session. This session involves safety, process, operation, plant layout personnel, to name a few. All possible hazards to which a plant could be subject are reviewed using a checklist. Hazards coming from the environment due to the location of the plant, for instance, is it subject to seismic event or climate extremes? Is there any adjacent industrial facility or transport corridor? The hazards linked to the products that are handled in the plant. The hazards link to the facility itself, such as large storage tanks or maintenance operations. Finally, the hazards for the working personnel due to the substance being handled. If any of these hazards are identified as a potential threat for the particular facility, a hazard action sheet is issued to the engineer. The hazard action sheet identifies the hazard and requests an answer from the engineer that this hazard has been taken into account. It could also provide a more specific recommendation. The HAZOP, which we have already mentioned about P&IDs, is a systematic review of the potential deviation of process parameters beyond their normal values. Is there a possibility, for instance, in the blue line, for the pressure to deviate beyond its normal operating range? Such possibility may be the failure of process controllers, failure of equipment, or operator error. If there is such a possibility, then the HAZOP will review, is there a safeguard against this too high pressure, such as a hard device, a pressure safety relief valve, or a soft device, an instrumented safety function? If there is none, then the HAZOP will request an action from the engineer. It will do so by issuing an HAZOP action sheet, which shall be answered and closed out by the engineer. Safety designs the plant fire protection and firefighting system. As we have seen in the plant layout, separation distances are kept within units. This segregation limits the extent of a fire within one unit, which is then called a fire zone. This helps to limit the capacity of the firefighting system to the needs of one fire zone instead of the complete plant. Within each fire zone, active and passive fire protection are provided. Active firefighting consists of spraying water on the plant equipment. Spraying water aims at cooling down the equipment so that it will not lose its mechanical strength and collapse. It also aims at absorbing heat from the fire to reduce its intensity. Spraying water can be done by several means. Spraying water on equipment can be done automatically by what is called a deluge system, or can be done manually by a fire monitor. A deluge system is provided systematically on all equipment of offshore facilities due to their close proximity. It is scarcely used offshore as access is available to spray equipment manually with fire monitors. Once the plant territory has been split in different fire zones, safety estimates the amount of fire water required for firefighting in each fire zone, and then takes the maximum amount among all fire zones to define the capacity of the fire water storage and pumping system. The fire water system is designed by safety by issuing PNIDs, which show fire water storage, pumping, and distribution. The system is also defined by safety by issuing its routing drawing, called the fire protection drawing. This drawing shows the route of the fire water distribution network. It is a ringed network that circles the facility and is provided with isolation valves at regular distances, so that a part of it can be isolated and repaired without affecting the remainder. Fire protection also includes passive fire protection. Passive fire protection consists of a coating of equipment supports or process structures or pipe rack, such as the one shown here with concrete for an onshore plant. For an offshore facility, this is not done with concrete for weight reasons, but with a special type of coating. To identify which equipment shall be protected with passive fire protection on their supports, safety draws the likely fire envelope and then identifies within this envelope the equipment which have a significant flammable products inventory. The safety of the plant also includes the possibility to shut down the process in an emergency, as well as to isolate and depressurize the various plant sections. Emergency isolation and depressurization valves are therefore provided throughout the plant to segregate the various plant sections and allow their depressurization in case of an emergency. Safety designs the fire and gas detection system. The fire and gas detection system gives alarm and executes automatic actions such as process shutdown, shutdown of building ventilation, release of firefighting agent upon fire or gas detection. Detectors are provided throughout the process areas and within buildings. The actions initiated upon detection are defined by safety on the cause and effect diagrams. Gas detection in the inlet ventilation duct of this building, for instance, is shown to stop the ventilation. The hazardous area classification consists of identifying the plant areas where a flammable atmosphere could be present. These areas are the areas around equipment and lines containing flammable gas and around equipment and lines containing liquids with flammable vapor, which means that they are at a temperature above their flash points. The extent of the hazardous area is specified in the codes. Safety consolidates the hazardous areas around all equipment and lines and draws the same in the hazardous area classification drawings. It then specifies that electrical and instrumentation equipment within a hazardous area must have an explosion protection so that there cannot be an ignition source for the potential flammable atmosphere that could develop in the area. The scope of the quantitative risk assessment is to assess the level of hazard created by the plant. The QRA consists of identifying the main risk scenarios and quantifying their probability of occurrence and consequences. The probability of an explosion, for instance, is the probability of leaks from various leak points multiplied by the probability of malfunction of the fire and gas detection system multiplied by the probability of the gas cloud reaching an ignition source. The consequence of an explosion is assessed by calculating the level of overpressure created by the blast at various distances. The product of the probability by the severity is the risk level. For each of the identified main risk scenario, it is plotted on this risk matrix. For instance, if we have a rather likely event with severe consequences, it will be in the red area, unacceptable risk area. In this case, the design must be changed. For instance, a blast wall must be provided. If, on the other hand, we are in the green area, no change is necessary, whereas in the gray area, called the ALARP area, ALARP, as low as reasonably practicable, the designer must prove that the design includes all the reasonably practicable mitigation and safeguards. The risk matrix is the one of the client, the company, the plant owner, or, in some countries, the one imposed by the authorities. We shall not forget to mention, in the various aspects of the plant safety, the need to provide escape and evacuation for personnel. This is of course particularly critical offshore due to the limited space and also the fact that the personnel is trapped on the facility and needs some evacuation means, such as lifeboats, to escape in an emergency. Let's look at the environment part of the discipline. First of all impacts of the plant on its environment must be identified. This is done by producing what is called the Environment Aspects Register. The second step is to identify which are the regulatory documents that apply to each of the plant emissions and which is the permissible limit, and is there any requirement, for instance, for continuous monitoring. The results of these investigations are collected in the Health and Environment Requirements Specification. This specification will be used by the other disciplines in their design. For instance, equipment will prescribe to machinery vendors the maximum pollutants limits that are shown in this specification for the exhaust stack of machineries. The Environmental Impact Assessment Study precisely quantifies the impact of the plant on the environment by presenting the results of dispersion studies of the various contaminants emitted by the plant on the environment. This concludes the presentation of the Safety and Environment discipline. Thank you for your attention. Goodbye.